Swayam Prabha. Digital India. Educated India.
Good afternoon and welcome you back to another lecture in this particular series on microscopy that we have been looking at. We already looked at the atomic force microscopy or scanning probe microscopy. Then we just began in the previous class towards the end regarding the electron based microscopy, and I have already explained you all these features in the previous class, and we will be focusing on two aspects. One is the transmitted electrons as the TEM and the secondary electrons as SEM. Okay, so if you look at the TEM, it is basically you use electron beam, very thin layer of the material or a surface of that, so with a high energy electrons, and then you look at the transmitted electrons out of that. Okay, so this is one of the very powerful technique where you can explore all the micro world or nano world, which is nothing but atomic scale and molecular scale kind of things. So it can go give information from materials to micron level, and in the simple materials, biological, everywhere you can use physical, biological materials. So it can provide, what are the information that it can provide? It can provide information about the size, it can provide about morphology. Additional things which you cannot get from AFM is the crystallographic information. AFM will not give crystallographic information at all. So what is the crystal lattice? We have already studied the XRD topic prior to this, so therefore you have an idea, the lattice types, etc., the space groups, all those kinds of things. So that is called crystallographic information or crystallographic parameters. All those can be obtained using the electron. There you have studied using the X radiation. Here you will be studying through the electron impact on that. Not only that, you can also get the elements. Okay, reason is we have already seen earlier also for the X radiation. The heavier the element, the greater the electron density, the greater the X-ray scatter radiation, and therefore the greater the strength of that. Similarly here for the electron also, the heavier the atom is, the greater the strength of the electron that come out in this. So there is a relation between the electron that is coming out versus the atoms. So therefore you can map in your sample what kind of atoms are there, the heavier, the lighter, etc. So therefore you can map all those things too. So then you can also do energy dispersive spectroscopy, as we have seen, the energy loss spectroscopy, energy dispersive spectroscopy, all of these as shown from these processes here. So you can attach different kinds of setups to the main TEM setup and then measure various things, actually a large number of things. So the TEM is again not one single instrument. The TEM is a family of instruments. So one major instrument is the TEM, and all other additional attachments can be made to that. So it is useful for characterization of morphology of nanoparticles. Light cannot give that, because the nanometric to the visual level a light cannot give. From nanometric to visual, if you want, you need the electron impact on that, and that's what you do. So the TEM is an impressive instrument with a number of advantages. So offers the most powerful magnification and resolution. As I said in the earlier classes, magnification alone is not sufficient. Magnification followed by the resolution are important. So that is what you will get. Provides information on surface features, shape, size, element, just now I've already talked to you here, and compound structure. Wide applications in biology, physics, and physical aspects, basically medical, materials, all those things. Okay, morphology, of course, can also be obtained of the nanoparticles, nanocomposites, any kind of things. High quality detailed images. So all of these are the positive factors for the TEM to be utilized. Okay, let us just look at one. As I said, that they use the high energy beam electrons on a thin layer. The specimen is as thin as a fraction of a micron. 100 nanometer is a fraction of a micron, 0.1 micron thickness. So that is the kind of thickness that you require. What happens is, if you have by unknowingly taken a little thicker, then the electrons get trapped, and then you will not get the proper TEM image, and then you will say that my compound is not giving TEM. That's not correct. So in the microscopy, sample making is one of the great art as compared to science. So that art is very important. In crystallography, the making the single crystal is an art, and that is what exactly. So when something is not shown in the microscopy, you cannot suddenly jump and say that this compound is not suitable for microscopy purpose. That is not correct. So you have to see various parameters, how you made, what is the thickness, so all those kinds of aspects. So you need to make a very ultra thin kind of a thing and then use that one. So you can use the photographic film, scintillators, all these using the charge coupled. Here is an example which is shown. This is a TM of image of a cluster of poliovirus, and the size is 30 nanometers. That is 30 nanometer size, each of the poliovirus particle. You can call that each one as one particle. See, very nice thing. And of course, this was a little early days, but now you can get even more resolved. That means you can focus on each of these particle and get some additional detail as well. Okay, and so why it is possible? Because in the light microscope, you're using the wavelengths of 500, 600, whereas you're using in the electron as a de Broglie wavelength. And that is the reason why you have this kind of a, and the resolution is also higher. So the magnification and resolution here. So therefore, TM becomes a good analytical technique for physical, chemical, biological, environment, everywhere, materials, everywhere. Okay, so as I said, the TM instrument is a housing, not only just the simple TM, many other things, the ELS, the EDAX, many things can be connected to that, the electron diffraction. So all those kinds of units can be connected and then made some changes and then measure all those things. For example, you can use for conventional imaging, scanning, tunneling, scanning TEM you can make, diffraction you can make, spectroscopy you can make, variety of spectroscopies that you've seen, a combination of all of these. So even within the conventional imaging, you can do variety of imagings. Image with the contrast mechanisms based on the position, thickness, density, on atomic number, Z contrast, and crystallographic contrast, which is based on the crystallography parameters, or diffraction contrast, or phase contrast, orientation, etc. That is called phase. So with respect to the beam and how the specimen is oriented, the specimen crystallites are oriented with respect to that, in just like we have seen in case of powder XRD, etc. And this is just a mesh on which you make a very ultra thin layer, as thin as 100 nanometers or even thinner, but greater the thickness, you will not get the diffraction. You will not get the TM picture. Okay, so let us look at some idea, because earlier we have also seen in case of AFM that the configuration, how it works. Now let us look at the two configurations given here. I draw your attention to this particular slide because I'm just making it in this, and of course the working principle can be checked from this particular link. You can always see there is a video, you can always see, and two of the configurations are given, one for the imaging mode, one for the diffraction mode. So if you stop that image part, some other apertures, and put a film or something, you can get your diffraction pattern. Okay, and also certain other non-diffracted things can be adjusted by adjusting the apertures. So allow the apertures to make flow through only the diffracting things. So you can do for imaging total things, and for diffraction only the diffracted electrons. So by instrumentational variation, which you don't need to understand in this particular course, people who are very specialized into that, they will learn, but just I'm giving as a idea to note, as a point to note in this. So this is the electron gun, that means source where the electrons are coming in, and then the condenser, the lens, the focusing, these are all magnetic lenses, not the optical lenses, they are magnetic lenses. So what they will do, they will condense and focus that. So make that, and you can see, and then you allow some aperture you can see. So only through, you can adjust these apertures. That is how you control a lot of things here. You can make the beam very fine focus, you can make the beam the width also. So therefore you can do, even you can do the with the TEM, with the scanning, so STEM, so that kind of thing. So that is where you can focus the beam on that. So whatever the way you require, these apertures can be adjusted a lot. So a lot of adjustments are there in this TEM, not that simple. And then this is specimen, means your sample. A sample, as I said, on a grid, as I showed you on the previous, this is the kind of a grid, and on this a very thin layer of that. Of course you will also have the grid also giving, so you can subtract those things and look at the informations. So that is where you have the specimen, and then once you go through the specimen, you have another lens focusing these electrons which are coming out, other objective lens. Then again you put the aperture, because you can use this aperture for allowing the non-diffracted to stop or non-diffracted to allow. So, and all those kinds of things can be. So diffraction, for those things you can adjust aperture, and then you can use the selected area apertures are here, and this is more important in case of diffraction mode, in image plane of the objective lens. Then you have the intermediate lens. The strength changes between the two regimes. So here versus here, there is some little changes there, and that's what makes for the diffraction in one case and the transmission in another case. So allowing not allowing the non-diffracted and allowing only the diffracted, and allowing all the electrons, and then you project to either to the detector or to the image plate or to the diffraction detector. So that is where this is a projector lens, and then the image plate or the diffraction pattern. So you have so many controls, you can control the force, the size, etc. You can control the focusing, you can control the apertures, you can control the objective aperture, objective lens, all these kinds of things. So you can also allow at this stage some kind of a back reversal kind of things, and then image. A lot of parameters are there, which I am not an expert in that, so but is not very important for this particular course, but just I am giving for that idea how complex when you look at these things coming in. So this is actually placed here, and this arrow is the electron gun. This is the electron is coming over here, and then you have 4th position here, 7th position here, and the 8th position here. These are all the ones where the lens systems are there, and you have a lot of knobs are here. You can adjust the lens, you can adjust the apertures, a lot of knobs are there, many things. Of course you can also control nowadays with all the software. So using the software, you don't need to use any of these hardware things. So you can control all these parameters, and then this is the viewing screen, and this is the controller, beam control, etc. So what level of beam, all those things can be. So all these things, whatever you see as a principle, you can see actual machine in that. And from here you can use a plate to get your image, or you can use a detector, CCD coupled detector, to get the diffraction pattern. So many things. So you can do a lot of and you can attach various other units to connect to the other one. So it's a family of the equipment that you have in this. Okay, here is an example where in the TEM you keep coming across the term called dark field, the term called bright field. So I thought I should clarify that. So this is a TEM figure, TEM picture for the platinum polycrystalline film. So platinum is a polycrystalline powder which is taken as a film, and this is the diffraction pattern. As I said, they use the aperture in such a way that only the non-diffracted one will be filtered off, then you can get the diffraction pattern. So the diffractions can be obtained. Already you've seen in the previous slide, the right side one is the unit which is made. But these are not different TEM machines. Same TEM machine you can adjust to get what you want. So in this, so you can see different regions. The regions of the center of this, the regions of this green, this one, the regions of this one. So these are all you can see. This is the where this is called the bright field part of it, and this is the dark field. So exactly reverse of that. So this is done by adjusting the scatter, diffraction. Here the details are given, which is not important. This is done by selecting a certain area in the back focal plane, such as only the central beam or a specific diffracted beam or a combination of these kind of things. So the instrumentation, you have to play with it. So therefore you can get accordingly. So these two are, this is the bright field and these are the dark field. So the rest is all dark and your object becomes the gray, and the rest is all gray and your object becomes dark. So that is what is the dark field, bright field kind of a things which. So at times people do both and try to sort of map your structural features, topographic features, etc. So DF, these are all there. Okay, diffraction I already mentioned to you. By using special kind of a parameters you can get the diffraction, and you can see the diffraction spots. So diffraction spot I already talked to you under powder X-ray diffraction, but and single crystal I have not talked to you, but this will be more like a single crystal because you are focusing on your beam, very fine beam, on a very particular position, and you are selecting a position and trying to get that one, and therefore you will have a crystal light. Therefore you will get a nice, as if that crystallize acts like a single crystal. So and then you can change this, tilt this particular sample, and you can get another orientation. So therefore using several patterns of these electron diffractions, you can get crystallographic parameters, like what kind of a lattice of this, what kind of a space group, all these information, whatever you get from the X-ray diffraction, you can also get from here. So the TM machine, which is a little modified kind of thing. So diffraction patterns, space groups, all the crystallographic parameters you can. And another little different kind of a thing, a complex behavior in the diffraction plane is also possible with phenomena such as Kikuchi lines arising from the multiple diffraction within the crystal lattice. Some of these spots could be coming from the different diffractions. Okay, so how do you separate them out? And that is what is done here. So in a convergent beam electron diffraction, this is called convergent beam electron diffraction. So you converge the beam and then look at that. So where a non-parallel converging electron wavefront is produced by concentrating the electron beam into a fine probe at the sample surface. So the interaction of the convergence beam can provide information beyond this particular information. So all these kind of information. So you can do the diffraction pattern, you can do convergent beam electron diffraction pattern to get further information. Reason is some of these spots what you're getting may not be from one single diffraction, could be from multiple diffractions coming in the same position in that too. But these are all extra details, but not necessary for this particular course, but necessary to mention the information. Okay, so diffraction, we are talking about diffraction. Contrast we have already talked about. So I talked about the lattice planes, etc., all those things, and the crystal lattice type and the space groups, all of those were. So that means we are in the world of the crystallography, but using the electron diffraction. Using certain specific kind of a instrumental changes, you can even look at the individual in a crystal lattice. There are some planes. If there are some planes are missing, if there are some atoms are missing, that's called plane defect, lattice defect, or the atom defect. All those kinds of things can be using the dark field or contrast microscopy or contrast diffraction. Using a contrast diffraction, contrast microscopy, you can try to identify not only just the lattice parameters and space group, you can also see whether there are whether that particular specimen has, in that region, everything is perfect, all the layers are there, or any of the planes are missing, any of the atoms are defected or defect atoms. So that is what you can identify from the diffraction contrast. So this diffraction contrast is measured by using the sample with respect to the beam in different angles with respect to that, because it's all, you know, that n lambda is 2d sine theta. Same thing is true even here as well. And so therefore the theta versus the 2 theta are the important parameters to look at that. So you can very specifically look at a particular plane. As the plane is there, plane is missing. Similarly, you can see the atom defects as well. So application for this method include the identification of lattice defects in crystals. So by carefully selecting the orientation of the sample, as I mentioned just now, it is possible not just to determine the position defects, but also determine the type of the defect present. There are a variety of defects are there. Those who have studied the solid state chemistry would have noticed all those kinds of things. Okay, so if the sample is oriented so that one particular plane is only slightly tilted away from the strongest diffraction plane known as the Bragg angle, any distortion of the crystal plane that locally tilts the plane to the Bragg angle will produce particularly strong contrast variations. So the contrast will come. From the contrast, you will find out there is a defect or there is no defect. So, but when the contrast is very small, it is very difficult to find out. However, defects that produce only displacement of atoms that do not tilt the crystal towards the Bragg angle, okay, so that will produce a weak contrast. So the greater the contrast, the better the way that you can find out. So in the TEM, using the diffraction contrast, you can find in the lattice whether some planes are missing, whether some atoms are missing, etc. with the contrast method. We already looked at the contrast. We already looked at the dark field method, the bright field method. Now we have looked at the contrast method. Dark field method, bright field method, contrast method. And all these methods you can try to use your specimen trying to rotate so that a particular angle gets matched with that Bragg angle so that you will see that particular plane. And if it is there, get the diffraction part of it. If it is not there, you will get the thing missing kind of thing. Okay, so similar way you can also do the three-dimensional imaging. So the three-dimensional imaging, what you will do, again you take the sample, you have the beam fixed, so you try to orient your sample. So by orient your sample, and also you will move to various positions as well. So you will make several number of such measurements and then combine them together, because you cannot reach in the TM 180-degree rotation. So that is where you make. So that is what is explained here. So actually you can take the 1 degree rotation with respect to the axis, 1 degree, 1 degree, 1 degree, 1 degree, like that. And in each case you take the image. So you take the data and you combine all that data. Okay. So and then there are some methods by which you can do. So mechanical refinement of such multi-axis tilting. At times when you don't have a full data collected in that, for example, you cannot go up to 180. So that will give some kind of a missing edge information in your the profile, in your image profile. Because image profile, if it has a full data, throughout the 180 degrees, it will give the complete one. If there is some of the data is missing, obviously you will have something called missing wedge of the data. So what they will do is, you instead of doing only with respect to one axis, you can also make with respect to another axis. So you can do that kind of a thing as well. The specimen. I talked to you these kind of axis rotations in the solid state NMR. So by doing that, you will reduce the breadth of the peak in the NMR. So here we are trying to get all the missing information so that you get a better image processing. So the mechanical refinement of such as multi-axis tilting. Two tilt series of the same specimen made at orthogonal directions, and conical tomography, where the specimen is first tilted to a given fixed angle and then imaged at equal angular rotational. So you put in this way and then make the rotations. You already tilt and make the rotation, another tilt and make the rotation, another tilt and make the rotation. So you try to get a kind of a conical type of a tomography. That's where the thing is. And with that, you can get the total imaging. There's another way of doing that is that, so suppose you take a protein molecule and make it into a dilute, very, very dilute solution, put onto this particular grid and make a thin layer. And you know that the molecules are dispersed at different regions and then they're fixed there, right? So, but they will not be fixed in same orientation. Same molecule is same chemically, but orientationally, geometrically, they are different. Now, if you can take the TM from each of that spot, each spot is one molecule because there's a couple of nanometers, and you can focus your beam of the couple of nanometers. So you can do each one of that and combine all of them, and you can get a three-dimensional image of that as well. So this is mostly used in biology now to get the even protein structures, virus structures, huge level structures which are not possible by crystallography at all. So now the transmission electron microscopy overrides the crystallography as far as the biology, as far as the virus, as far as the multicellular complex is concerned, all of these. So one is by varying, rotating with respect to an axis, or tilting and rotating an axis, etc., you can get the image. The other one is that you can have the spot, your TM, taken at different spots, a large number in fact. I'll show you some examples at a later stage. And you combine all of them and convert into an image. So you can get a full image of that. And this is what is mentioned over here. So what you do is, so single particle analysis, particle by particle, particle by particle. So you measure for each of them, and they are all not in words. They are all chemically same. The molecule is same, but their orientations differ when they got settled on the surface. Okay, because they are randomly pressed in because they are brought into that state from the solution. In the solution, they were freely moving, and when they are brought to this thin layer, they've been frozen. Okay, and that is where the they use images of multiple identical objects at different orientations. So to produce the image data required for three-dimensional reconstruction. So if the objects do not have significant preferred orientations, this method does not suffer from the missing data wedge which accompany tomographic methods, nor does it incur excessive radiation damage. So however, it assumes that the different objects imaged can be treated as the 3D data generated from them arose from a single stable object. So when you combine all of them, it will be equivalent to one of those. That is how you do that. So in this you can do two methods. One is the TM, other is the STM. So these two are reciprocal in terms of their methodology. So this is for the TM and this is for the SEM. Here the point source is coming from this direction, and in the STM the point source is coming from this direction. And if you look at this particular thing, condenser, aperture, etc., this angle here, and that angle is coming from this side, not from this side, not from point source side. So this one line here is equal to this one, and these are not same, because this is from the source side and this is from the detector side. So this is the source side, but this is the detector side, and the other angle here is on the detector side and that is on the source side. So exactly reciprocal type. So a TM, STM, okay, are linked by the Helmholtz reciprocity, so which is basically dependent on this. The STM is basically a TM in which the electron source and the observation point, that is the detector, have been switched relative to the direction of the travel of the electron beam with respect to that. Not just simple physical switching, with respect to electron beam, the travel. So you can see all of these, okay. That is where you can use, so these two techniques are measured. So in the next class I will take up the examples, how these TM samples can be analyzed, how they will help you in understanding, and once we complete that, we will focus on the SEM part of it. And thank you very much.